Thank you. Thank you so much, Alex. Thank you all for coming today, this afternoon. Really excited to talk to you all about my favorite rocks, the Martian rocks. So really, the main goal of my research is one of the main goals of my research is trying to understand how did the Martian interior and surface evolve through time. And for that, to address this main goal, this main question, I use meteorites, which are the only samples that we have from Mars, as well as rover data to answer this question. So, okay, so before I talk about any of the research, like most of the research I present is from my students. You see them all here, my present student and my former student. So most of, again, what I'm presenting is their work, their hard work. And then also, I'd like to thank all my main collaborators for all the fun things that we get to do together. And you can see most of them are holding meteorites in their hands. So first, what do I do? So I'm a igneous petrologist, and I really study space rocks the same way that terrestrial petrologists do. But I study Martian igneous rocks. So what about meteorites? When I have a meteorite, the first thing I do is I look at it under the microscope. As you can see right here, this is a nuclide. This is a type of Martian meteorite, just to look at its texture, the grain size, the grain shape, the mineral abundance. And this can already tell me quite a lot about this rocks and how it was formed. And then we can look at it under some very typical instrument that we have, like a microprobe, for example, that can tell you about major element composition, or in what we call the Arya ICP-MS, so this laser ablation mass spectrometry to look at trace element within mineral. And all of that can tell you a lot about how those rocks form. And also study surface igneous rocks, but with that, unfortunately, I cannot look at them in the lab. I look at them with a rover directly on Mars. So today I'm going to tell you first about Martian meteorites. What are they? What have they told us about Mars? And also, I'm going to talk a little bit about what they can tell us about the emplacement in the Martian interior and the surface, even without field context. I'm going to tell you about surface igneous rocks, and finally, we'll talk about a little bit Jezero crater, Mars 2020, and why do we need return samples, which is really a big question that we have right now. So to start, if you don't know really what meteorites are, if you're not really sure, so meteorites are just directly ejected from the parent body, so in this case Mars, through impact. So imagine another meteorite impacting Mars at a speed high enough that it will eject a piece of it into space, float into space, and then land on Earth. So we have meteorite landing on Earth all the time, but it's easier to find them in the desert when you don't have vegetation or other rocks. There's actually places where you can find is Antarctica. So there's the NSMIT mission. So you can see here, this is a colleague, Dr. Neil Lenza, with this meteorite right there over there. This mission is a mission that's, the NSMIT mission goes to Antarctica 2 months per year, every year, minus COVID, obviously. And it's constituted of 8 volunteers, usually planetary scientists, there's 2 mountaineers, and they go around on the ice on the skidoo and look for meteorites. And really, there's some terrestrial rocks, but it's mostly what you find there are meteorites. And they just came back. My former PhD student, who's a postdoc right now at the Smithsonian Institute, is already looking at them right now. Hopefully, there's a new Martian in this year's campaign. But so those samples belong to the US government, but myself as a scientist and yourself as graduate student, if you want to work on them, you can write a little proposal explaining what you want to do with them. Are you going to do any destructive techniques or not? And then, if you want a thin section, do you want a little chip of it? And then a group will decide if you get it or not. And usually it's not like a proposal like money. NASA want to give you the sample, obviously. That's why we go look for them. Another way to get meteorites is meteorites from Northwest Africa. So most Martian meteorites actually come from the Northwest African desert. Again, there's not that much vegetation there, and you can see those meteorites really pop out in the middle of the desert. So usually those meteorites, they are collected from locals, the full-time job is to go look for meteorites and then sell them to private, to dealers that then will sell them to collectors or scientists like me. So I work with a few meteorite dealers that say like, hey, I have this type of meteorite, do you want it? I will put this one also as well in it. But I can also just borrow it from my colleagues who especially have museums. So, you know, I borrowed meteorite from PSU, from University of New Mexico, from Field Museum of Chicago, and all that is for free. We just all work together and collaborate. So the question I always have is, how do we know Martian meteorites are from Mars? So the first time it was mentioned was back in the end of the 70s, was actually Max Sweet, and who was my PhD advisor, and Ed Stolper, who looked at this meteorite that looked a little bit different from the other, because most of the meteorites that we have, actually all the meteorites that we had at that time, came from the asteroid belt, which is, you know, located between Mars and Jupiter. But this one was a little bit different. It was younger. The mineralogy and the composition looked like it came from a much larger planet. And then in the beginning of the 80s, Bogart et al. Looked at those little gas inclusion within pyroxene, so within mineral, in those same meteorites. And they compare it to the Martian atmospheric composition that was measured by the Viking landers back in 1976, and found that the Martian atmosphere composition and the meteorite gas composition for nitrogen, CO2, and noble gas was exactly the same. So this was the first time we had like evidence that we had Martian meteorite. And now we use tools that are a little bit more easier and cheaper to do. So we can look at triple oxygen isotopic composition of those rocks, because the triple oxygen isotope composition is the signature of the parent body, because in the solar system there's kind of a pocket of isotopic composition, and also other elements. So for example, Mars is more enriched in iron and sodium compared to the Earth. There's not really a good reason for that. It's just when the solar system formed, that's where it was concentrated more, where Mars formed. So it's kind of the same with triple oxygen composition. So this is how now we know like for sure that we have a Martian meteorite. So with meteorites, we can constrain a lot of different processes. First, we can, like I do on a daily basis, constrain the emplacement and formation of magmatic rocks. We can better understand volcanic processes, the diversity of sources. And when I talk about sources, I talk about chemical reservoirs. So for example, inside the Earth, we have a lot of different geochemical reservoirs. I mean, if you just look at the crust, the depleted mantle, the undepleted mantle, those are different reservoirs. They have different trace element composition, different isotopic composition. And it is actually the same on Mars. We can better understand volatile processes, alteration processes. I don't personally look at those in detail, but they're really important. Impact processes, and finally the timing of all of those different processes, because meteorite are samples that we can analyze in Earth-based laboratories and very high precision, high accuracy labs. So before I keep going, we're going to do a little Martian interlude. This way you can know a little bit more about the terminology of everything, because I'm going to mention a few words. So first, for those of you who are not good at petrology, or more like doing hydrology and those kind of things, let me remind you a little bit what kind of minerals we expect in Martian meteorite, and they're really the same that what you would expect in terrestrial basalt. If you go to Hawaii, you'll find the same thing. So what we have olivine, rich in magnesium, as well as iron, pyroxene, that's rich in more iron, magnesium, and calcium, and then plagioclase, which is enriched in aluminium, calcium, and also a little bit of sodium. Then you have minerals like oxide, phosphate, sulfite, very typical stuff that we find on Earth. That's what are in Martian meteorite. So I will mention olivine, pyroxene, and plagioclase, or plage. And then what about the ages? So on here, we compared actually the Earth timescale on top and the Mars timescale on the bottom. And you can see there's three main ages on Mars. There's the Amazonian, between 3 billion years old, and now not that much happened during that time. We have the Hesperian between 3 billion and 3.6 billion, and then the Noachian between 3.6 4.1. Sometimes we include an Noachian from 3.6 till 4.5. So the really beginning of the Martian geological history. And really what happened, impact, volcanism, possible water, maybe even life likely happened during the Noachian, during this blue and green period right here. So remember, Noachian, is old, Hesperian, a little bit old, Amazonian. It's kind of most of the Martian geological history, but not that much happened during that time. Okay, those are 3 ages. And one thing I want to show you on this map, this are all different ages, and what you have, the Noachian, is everything that's green, green, and brown. And you can see this is actually more than 50% of the Martian surface is older than 3.7 billion years old, which makes sense because there's no plate tectonics on Mars. Okay, one thing to remember. Okay, so what about meteorites? Right now we have 246 recovered Martian meteorites. As of today, I just recalculated that 2 days ago. And on this graph, you can see in x-axis all the meteorites that were found, when they were found or classified. The first one was found in 1815. It's called Chassigny, and it was found in central France. And y-axis, obviously, you have the number of meteorites and all the different types of Martian meteorites. And you can see one thing I want you to notice, since 2011, most of the Martian meteorites were found, really most of them, which is good because it's when I started my PhD, perfect for me. Obviously, there's a decrease a little bit since COVID and it stays still the same amount, but we still have, you know, about an average now 17 Martian meteorites that are discovered every year, which is great. And some crazy one, for example, this brand new vesicular basalt, excuse me, which I'm very excited about, just got classified. We don't have anything vesicular from Mars. So there's 3 main groups of Martian meteorites, what we call the chagotite, the nuclites, and the chassignite. Some of you might have heard before the SNC, and the name are based on the first specimen that was found. So chagotite, the first one was found in Chagoti in India in 1965. Nuclites, the first one was found in Nukla in Egypt in 1911, I believe. And then Chassigny, the first one, chassignite, the first one was found in Chassigny in central France in 1815. All of them, you know, are igneous, the magmatic, the pretty much basalts, and all of them, all the chagotites, for example, the chagotite is the most common type, and they were found between 2.4 and billion years old to 150 million years old, but there's really not that much between 2.4 and 500 millions. And then all the nuclites and chassignites are 1.3 billion years old. So really, most of the Martian meteorites that we have are between 1.3 billion years old to the present, which is quite different compared to what we have the Martian surface. And then we have 2 meteorites that come from the Noachian, so very old. Allen Hills 84001. It's also magmatic. I'll tell you more about it. It's 4.1 billion years old. And then the beautiful Northwest Africa, or NWA, 7034, and it's paired meteorite. By the way, when I say paired meteorites are when you have the main meteor, it's called meteor, when it hasn't landed yet, and will break down when it enters the Earth's atmosphere and become several pieces. Those several pieces are paired meteorite. So there's 18 of them actually for NWA 7034, and it's a beautiful Ptolemaic regolith breccia. It's the only sedimentary one, which mostly actually represent impact and volcanic processes. It's gorgeous, and I'll show you more about that. So the one main issue with Martian meteorites, they're really cool because they likely come from all over the place, but we don't know from where. Okay, this is a topographic map of Mars. You have in blue the lowest elevation in, for example, Hellas Basin, and in red you have the highest elevation, and we don't really know where they come from. We know that we have more than 11 ejection sites based on the ejection age, but that's kind of all that we know. There has been some inferment of ejection craters, but it's really hard to have evidence of it, true evidence. So let's look at the different type of Martian meteorites. So the first one, like I said, chagotite is the most common type of Martian meteorites. The basalts, the peridotites, the gabbro, and they range in age from 150 million years old to 2.3 billion years old. And this is a very typical one that you find here. This is actually gabbro. It's called NWA 6963, and what you can see here, this is an elemental map. When in red you have iron, in green magnesium, and in blue calcium. It's just a bunch of different pyroxene and some shocked plagioclase in between. It's a nice example of one. Then there's also the nuclite and chassignite. They have those 2 groups. Actually, the nuclites are clinopyroxene rich, cumulate rocks. In this, you can see a lot of pyroxene with some olivine right there. Whereas the chassagnites are donites, so they're mostly made of olivine. And those two groups have a lot of geochemical similarities, and they have the same crystallization age of 1.3 billion years old and the same ejection age. Again, right now we have 35 individual rocks in total. And because they likely come from the same spot because they have the same ejection age. So, you know, the chance for two impacts to happen exactly at the same time and eject the same time and then land both, you know, all land on Earth is low. So we likely all come from the same ejection spot, which means that we can all study them as suite, which is really exciting because, you know, those of you who are terrestrial geologists, when you go in the field, you don't just take one rock home, you know, just go in the field, take one rock and go home. You take a suite of rock, and this is what we can do with those. Although we don't have the exact outcrop field context, we at least know that they come from the same volcanic place. There's also Allen Hills 84001. This rock is also pyroxenite. It's cumulate. It's very old. It's 4.1 billion years old. But what's really exciting about this rock is that it was argued to prove life on Mars. So actually, there's little magnetite in this rock within low calcium carbonates. And those magnetite, it was inferred in 1996 that they form by possibly like magnetobacteria. Magnetobacteria are bacteria that we find on Earth that form and create magnetite. And because of that, even if later on, because of the structure and the composition, it was disproved that those magnetite and calcium were abiotic, it was still, you know, was a big deal. Bill Clinton went on TV and said that we have found life on Mars. And it really pushed forward the Martian exploration at that time. So in 1997, we had the Pathfinder rover, and then the Spirit and Opportunity rovers in 2004. And in 2012, we had the Curiosity rover, and then 2020, you know, and we had Mars 2020. Then we had a bunch of orbiters as well. So this is when we really got started to be even more excited about Mars. So this is a very important rock. And then finally, we have this beautiful polemic regolith breccia NWA 7034. What's really exciting about it, it has a bunch of different clasts in it. You can see that polemic means that those clasts really likely come from different sources. And what's also really exciting is that those clasts are the oldest igneous clasts that we have from any terrestrial planets. Some of those are 4.5 billion years old, which is older than the Jack Hill zircon that are 4.4 billion years old, which are the oldest minerals that we have from Earth. You can see right here, this is a beautiful class that we took with our new SEM. And this is a backscatter electron image. Pretty much, it tells you, you know, it's based on the atomic numbers. So whatever is white has like a higher density. So it's going to be more like oxide. But you can see pretty all this is plagioclase in dark gray and pyroxene in lighter gray. But you can see that it's quite complex. It is very shocked as well. I mean, this rock has been there. I mean, those clasts and this rock has been on Mars for a long time. So it's been shocked and bombarded and, you know, reworked a lot by impacts. But this rock can tell us a lot about the very early magmatism on Mars and can be kind of an analog to our early Earth because we don't have any rocks from the Hadean. So I want to tell you now a little bit more about emplacement of those rocks, in particular, my favorite one, the nuclides and the chassagnites. And those, remember, those are the ones that likely all come from the same volcanic province. So what we can do is we first looked at the quantitative textural analysis, which means that we measure actually the grain size, the grain shape, to understand how they're all in place. We can do that on Earth, but also we can do that on Mars when we don't have field context. And this is some of the conclusion that we came to. Before 2018, it was shown that they all came from the same cumulate pile, the same lava flow, and it seemed kind of strange. And with the recovery of some new Martian meteorite, it did not look right, the succession within the same lava flow. And we showed that they likely come from different flows and actually very likely from different seals. So they're likely intrusive. They were formed beneath the Martian surface. And we also looked at, you know, different things like ejection age and chemistry to better understand you know, how they were formed and what were the different groups. But then remember, we're just looking at one thin section to infer like a whole volcanic province. But we don't have much with Martian meteorite. The thing that we can do is do three-dimensional X-ray computer tomography, which is pretty much doing a CAT scan of your rock. And this is something that my PhD students here at Ramsey is doing right now. So this is what you can see when you do XCT analysis. This is another nuclide. So in dark gray, you can see actually plagioclase, and light gray right here, you can see a bunch of pyroxene, and even lighter gray, you can see those olivine. But you can see the shapes are changing a lot. We can see, oh, no, I need to stop touching my mouse. Is it working? We can see also some, well, they melt inclusions. You can see a little inclusion of trapped melt that happened in those olivine. So many different textures, some crazy oxide are appearing right now that are relatively skeletal, so likely form quite fast. But you can see like each of those images represent one thin section. So imagine you pretty much have 1,000th section to look at, and you can truly see the real shape of your olivine, of your pyroxene. Actually, those pyroxene in those look like rods and not like just a single little rounded thing that you can see on here. So they're quite complex, and we're trying to see what we can tell. Do we see any foliation, lineation at the bit? And that can tell us more, like, did it form a magmatic chamber, did it form a lava flow? This is what we've been doing with those. And XCT is really the future of petrography, truly. One other thing that we can look at, you know, I mentioned melt inclusion. Melt inclusions are little trap pockets of magma that you have within your early crystallizing mineral, and they can tell you much more about the parent-hole magma of those rocks. So we can look at major element, but also trace elements. So on those graph, I divided the nuclides and chasignite and the chagotites, so 3 different groups of Martian meteorite. We looked at certain trace elements, zirconium over yttrium, and niobium versus yttrium, same thing for the chagotites. There's a lot happening right here. Don't worry about it. You can see on here, you have all those envelopes representing the bulk rock composition. What I want you to notice for the chagotites, the points are much more gathered together, and that they correspond, the melt inclusion composition correspond much more to the bulk rock versus the nuclides and chasignite. It's all over the place. And with that, we actually concluded that because the trace elements are all over the place, they had to have some diffusion. So if you look at the melt inclusion, you probably had some, you know, trace element going from one side to the other, just diffuse with time. And diffusion happened, especially with those trace elements. Trace elements are not really supposed to be mobile. They're supposed to stay where they crystallize. We think that they were stored in a magma chamber for a very, very long time versus the chagotite that did not happen. So that's one thing that we can do with those Martian meteorite, again, without having any field context. We can do also look at minor element distribution. So those minor elements like phosphorus and olivine and chromium and pyroxene, those are, they're not mobile. Again, they do not diffuse much with time compared to magnesium and iron that diffuse really fast with time. So we can look at them. So if you look at the chromium map in this pyroxene, this is a heat map. So red is really high and blue is less high. You can see we have this kind of Swiss cheese texture and those different layers for this pyroxene we see. And actually we see those exact pattern all over all the different nuclides. So we first know that they all had the same emplacement process, same emplacement steps, and we can kind of infer also a little bit more about the magmatic history looking at those minor elements map. So, you know, Martian meteorites, I hope I showed you, they can help us to better understand the Martian interior and surface. And actually with time, we've been having more of this diverse lithology, which is quite exciting. We have emplacement that's actually quite similar to terrestrial and terrestrial igneous rocks. And actually we have a Martian interior from that. We've inferred that it's more heterogeneous than previously thought, which is quite exciting. But there's a limitation with those. Those rocks are all very young. The younger 1.3 billion years old. And remember, I told you that most of more than 50% of the Martian surface is older than 3.7 million years old. We also have a biosampling of the crust. The composition, the bulk composition of Martian meteorites are slightly different than what we found at the surface with rover. We also have no field context. We know that they come from Mars, but that's about it. That's it. So we can infer what's happening at the AdScope scale, but maybe everything I'm telling you is completely wrong. I hope not, but it might be. And we're also lacking the true lithological diversity. Well, we don't have any sedimentary rocks, but also just igneous rocks. We have found alkaline-rich rocks, felsic rocks, so silica-rich rocks at the surface. We have not found any of that in Martian meteorites. So things are missing. So really, what about the igneous rocks from the surface? What do we have there? So if we go back to our topographic map, where you can see everything that's in purple are different landing sites of lander and rovers. So I'm going to talk about places where we have igneous rocks, because again, this is what I do. Gusev crater, where Spirit rover landed in 2004. Gale crater with Curiosity rover landed in 2012, and then obviously Jezero crater with Mars 2020 landed. And I say obviously because I'm actually part of the Mars 2020 science team, so I've been working a little bit on those igneous rocks. So there's igneous rocks everywhere. There's some in Gusev crater. Actually, we landed in Gusev crater thinking that it was all lacustrine. It looks like a little, I don't know if you can see, actually you cannot see. It looks like a little lake. So everyone think it was sedimentary rock. We landed there and ta-da, it was actually all basalt, which is great for us igneous petrologists. Curiosity rover landed in Gale crater and we had some crazy cumulate rocks. You can see those beautiful plagioclase right here. And the scale says 5 centimeters from here to here. And then Jezero crater, the first year, we all find igneous rocks, which was quite exciting. Those two are really basalts. So the problem with igneous rocks or rover analysis, there's also limitation because it's difficult to conduct precise mineral analysis. We cannot really see. It's not like going in the microscope. I'm showing over there because my microscope is right there. But I'm quite often on my microscope and I need to be on my microscope to understand, the context of those rocks. And also we don't have a resolution analysis like you would do, analysis in the lab here when you have to do, clean lab analysis. So really what we need is state-of-the-art geochemical and petrological as well as geochronological analysis, things that can be done in the lab. So for that, we need return samples. We need to have the field context that we can have with a rover looking around on the outcrop and also even larger scale context. And then we need to bring back those rocks at home on Earth to be able to date those rocks, to do precise Earth-based laboratory analysis. And hopefully, right now, this is what we're doing at Jezero crater that you can see in the background with the Mars 2020 mission. It's going to look at rocks that are from the Amazonian to the Noachian, from young to old. Larger lithological diversity. We have igneous rocks, we will have sedimentary rocks, and even the igneous rocks. We might have the Noachian crest, and I'm, praying the Martian gods to have felsic rocks. That would be absolutely amazing. And also from that, because we can date those rocks, we can have a better definition of Martian crater ages. Why do we care about that? Because in planetary science, we date surface of planets and asteroids using crater counting. So crater counting, think about it, the whole way to do it is like we look at the surface. If you have a brand new surface, there's no crater on it. The older it is, the more crater you're gonna have. So you can date it that way, but for that you need calibration, and everything is calibrated with the moon because we went to the moon. We knew what surface we were on, we could count the craters, but we went there, with the Apollo missions, collected those samples and dated back on Earth. And this is how we calibrated them, except on Mars, but Mars is in a different location in the solar system. It has undergone different impact history as well. So we need to calibrate our crater counting technique to Mars. So return samples. Hopefully, this is the start of the Martian return sample mission is Mars 2020 and the Perseverance rover that you can see right here. It landed in Jezero crater on February 18th, 2021. You can see very proud. It has drilled some rocks in Montpesa. That's the name of this rock right here, which is a beautiful igneous rock. So the first year, we looked at 2 rocks formation that were igneous. So right here, you have the Octavia E. Butler landing site. So it went there. And actually, you can see all those as Sol. Sol are Martian days. They're almost like Earth days, but they are 24 hours and 38 minutes, which is just a pain, just long enough to be a pain with science operation. So the first formation it was in the Mars formation. So it is called Mars because this is the Mars in the Navajo language. So when you go on a planet, especially on Mars, you can divide where we land, you divide everything in quadrant, and each quadrant has a name of a location on Earth. This location right here on the top, right there, is Canyon de Chelly, which is in Arizona on Navajo land. So all the rocks that we name are all using Navajo language. And we've worked with Navajo Nation, and there's actually a member of the Navajo tribe that is part of the Mars 2020 science team. So Mars formation means Mars, and then we enter, that's all pretty much 201, the Zeta formation, which is a bit different. Zeta means actually amongst the dune in Navajo. We went back, and then we went back up, and all of that in a year. Okay, and we have collected a few samples in the Mars formation and in the Zeta formation. Those two are different. Mars will have mostly basaltic lava flows, whereas Zeta is more cumulative olivine formation, which is all quite very exciting. So the main question that we first had is the Mars formation igneous? This is the main question when you're on a mission, on the Martian mission, is it igneous or is it sedimentary? And I can tell you the debates are long and painful. So I mostly looked at SuperCam analysis. SuperCam, this is the instrument that has the coolest one because it has the laser, obviously. And at SALT 379, when we left those igneous formation, it has collected 1,057 ellipse point. Ellipse point is laser-induced breakdown spectroscopy. This is those laser. And then looking at also 114 target in the Mars formation. And by the way, LIBS, what it does, this instrument is quite fun. It's always remote. So it can be from 2 meters or 1.5 meters to 7 meters. You will shoot this laser to the rock. The rock will become plasma. That plasma will emit a light. And this light will have a spectra that we can measure and translate into geochemical analysis. So it's kind of like having a little microprobe. So first we looked at textures. This is the first thing, this is what I look on my Martian meteorites, what petrologists look at, and there's a lot going on here. We had a lot of different texture, very fine grain. We had pitted, look like vesicles. We had non-pitted, but like coarser grain. And all of those different textures really reminded us of what you see, this diverse texture that we see in lava flow. So a very likely effusive lava flow, as well as coarser texture. So it has to be thicker because usually it's going to be coarser grain in the middle and finer grain and vesicular at the top. And I'll show you a little graph about it. This was kind of one of the first things we looked at. And you can see also igneous texture that we've seen, like this look like a Paihoi texture that you will see like in Hawaii. Beautiful lava flow texture, as well as this is from the Zeta formation. This sample is called Scene. That's actually not Navajo. We're just in the quadrant that's called Vaucluse, which is in southern France, which is, France is where I'm also from. And so all the names are in French, and it's quite fun to learn all those funky names to Americans. And you can see here this beautiful cumulative texture. So really likely all igneous. But now let's look at the composition. So there's a lot going on this graph. Don't worry, this is about composition of everything. So you have here silica and alkali content, magnesium versus aluminum versus calcium versus iron. All the rainbow colors, this is all meteorites. And what you see, the bigger signs in orange represent the Jezero Jezero crater, the mass, actually, the mass formation analysis that we had. And what you can see is that it's a little bit less rich in magnesium, which also a little bit less aluminum, but mostly enriched in alkali elements compared to most Martian meteorites, except maybe the regolith breccia, but the regolith breccia is funky. So slightly different composition from Martian meteorite. We can also look at the mineral composition. So because LIBS is a laser, and if the mineral are large enough, we can see if we have hit them or not. We do a lot of stoichiometry calculation to see what mineral composition we have. But right here, you can see this is a really typical pyroxene quadrilateral. On the left, you have magnesium. On the right, you have iron. And on the top, you have calcium. All of those funky colors, again, those are all pyroxene for Martian meteorite. And what you see in red, the bigger grain, the bigger symbols here, this is all the mass formation pyroxene. They are very rich in pyroxene, very rich in iron, which is really quite weird, which is not what we expected. Even if our calibration is wrong, even if there's a big error, it's still very rich in iron, which is quite interesting. We found one plagioclase right here. We think the plagioclase is too fine to be analyzed, but it also looks like the other Martian meteorite. So we really, with the texture, the composition, we think that the mass and the zeta formation are igneous. Again, with the mass formation corresponding to a thick lava flow with coarser grain composition in the center where it stays hotter, longer, whereas at the top and the bottom, you have more a vuggy, more pitted vesicular texture representing the gassing, as well as more fine grain as well, and also that pyrohoi texture. Whereas the zeta formation likely represent more like olivine accumulation below. We don't really fully understand yet the relationship, the link between those two. But it's interesting. Also, we could have also potentially found pyroclastic flow really with this laminar layer texture. So the mass formation is igneous, but somewhat similar to Martian meteorites, but slightly different mineralogy with really rich, iron-rich pyroxene. Cannot wait to see them in the lab. Different bulk composition. But because of this difference, they are important for sampling. Well, they're first important for crater counting, like I explained before, but also for igneous activities because we have different composition and likely different ages compared to what we found in the Martian meteorite. We have not looked at the trace element composition. We cannot do that. So what is the composition of the sources, for example? So right now, we have 8 igneous rocks that have been collected. For example, you have Mondoni and Montagnac that have been drilled right here. You can see Montagnac, that's when it entered the cache. But that's not only that. We mostly actually have sampled sedimentary rocks. We have 10 sedimentary rock, we have sandstone, we have siltstone, we have also 2 regoliths, so the soil, the top surface of Mars. We have also 1 atmospheric sample as well. So in total, we have 38 sample core that we can use, and then 5 also witness tube that look at this kind of calibration to make sure that the sampling system is actually not contaminated. So for the moment, we have filled up 60% of our cache, our sample tubes that look about the size of a chalk, you know, those white chalks. So again, 10 sedimentary rocks, we have none of that in our Martian meteorite collection. So actually, there's 10 backup samples that were deposited at the Three Forks Sample Depot. So in case the rover gets stuck somewhere and cannot deliver it gets stuck in an area that's not accessible to other spacecraft to be able to bring back the sample back home, they've been deposited in an area where it's easy to land, which is called the Three Forks Sample Depot. So we have 10 of them right now that deposited there. There's still a lot inside the rover, but those have been deposited if we want to bring them back, and you can see them all on this image. So the Mars sample return program is in multi-steps. So first we have Mars 2020, where we need to bring those back. The rover is not just going to take off by itself and go home. So what's going to first land on Mars at the end of 2020s, it's going to be the sample retrieval lander, SRL, that will retrieve the sample that Perseverance can drop off. We can also have 2 little helicopters that can help with those as well and bring them back to the sample retrieval lander. The sample retrieval lander will then put those samples into the Mars ascent vehicle. That's pretty much a big rocket that will launch into space. And in the Martian orbit, the Mars ascent vehicle will be intercepted by the Earth return orbiters, that is ESA spacecraft, so Earth's European Space Agency spacecraft that will then come back to Earth, and then we'll finally land where we think in Utah. This is where return samples land. So I don't know if you all heard about the OSIRIS-REx samples that all came back from the asteroid Bennu. They landed in Utah. So usually they land. And then we'll be able, that should be 2033, a little bit later, and then we'll be able to analyze them in the lab at home. So where are we right now? So you can see this is the Jezero crater. It has a giant delta, and that's one of the reasons we went there, because sedimentary rock, and then also very fine-grained sedimentary rock, so we can have potentially biosignature in it, and which are evidence of ancient life, like stromatolites, beautiful biosignature. So this is where Zeta and Mass were, and just went then into the delta, went out on the margin of the delta, and then we're going to go into the crater rim, which hopefully we can find some really old Noachian crust. We are now in Sol 1055 already, and it has gone a distance of 15 miles, which is quite crazy. And Ingenuity is here in the dunes, and it's going to stay there. It just died in last week. So congrats to Ingenuity for everything it did. So I just want to show you this cool picture. This is a big dust devil. Maybe some of you do atmospheric work. Look at this right here. This is kind of what we have right here at home. It's quite high, and it's just a few miles and maybe a mile or 2 in height. It's quite a beast. And actually aeolian processes are very, very big on Mars, because, you know, no water, but a lot of wind and a lot of dust. So hopefully I convinced you that we need return samples to really understand the Martian geology. We have 38 samples that we come back to Earth. We have diverse lithology, we have sedimentary rocks, and also igneous lithologies with different composition from Noachian to Amazonian. And really, we have Martian meteorites. They're really important to still study. They come from all over the planet, and they tell us something else as well. And the complementary study of return samples and meteorite will help us constrain the evolution from the Noachian to the Amazonian of the Martian interior. And most of you right here are not Martian scientists, okay? Actually, pretty much all of you are really not Martian scientists. You'll tell me, why do I care? Well, actually, it's not only for the Martian community. It's really for everyone, for all geoscientists. Mars is a beautiful analog of, you know, the very young Earth. We don't have good record of the Hadean, nor really of the Archean. And this Mars can tell us much more about young Earth, because it didn't have plate tectonics. And even, like, you know, we have an atmospheric sample. This sample will be studied, and we'll be able to better understand the evolution of Martian atmosphere, and thus better understand the atmospheric evolution of the inner planet, and then extrapolate that to the outer planet. So really, by looking at, you know, in context of our Earth sample, Martian samples, we also have the moon, we can really better understand the inner solar system, but then the entire solar system. And this is why, you know, it is important to bring back those samples. Thank you all very much for your attention. I'll take any questions that you have.